Coulomb's law in the magnetism. Now, Coulomb's law in magnetism states that the force of attraction or repulsion between two magnetic poles of strength m1 and m2 placed at a distance r apart is directly proportional to the product of their pole strengths and inversely proportional to the square of the distance between them. So this Coulomb's law is in magnetism is similar to Coulomb's law in electrostatics. If we can recall in chapter 1, Coulomb's law in electrostatics, the force of attraction or repulsion between two charges q1, q2 separated by a distance r is given as F is equal to k q1, q2 divided by r square. So here also, instead of charges, we have two magnets, one of pole strength m1 and another one is of pole strength m2. And as shown in the diagram, since a monopole does not exist, we don't have just a south pole or just a north pole. Since magnets, they always comes in pair, so we have always north pole and south pole. Okay, so here we have this magnet. One is of pole strength m1 having north pole and south pole, and another is this magnet of pole strength m2 having the north pole and south pole. And you can see here that the north pole of one magnet is separated from the south pole of the other magnet by a distance r. So there is a force of attraction between these two poles, south pole and the north pole, and that force of attraction is directly proportional to the product m1 into m2 then divided by r square, or inversely proportional to the square of the distance r. And if we remove the proportionality sign, we have F to be equal to k m1 into m2 divided by r square, and this k is equal to mu naught by 4 pi, and this mu naught is called the absolute permeability of free space, and in SI unit, this mu naught is equal to 4 pi into 10 to the power minus 7 Weber per ampere per meter, where this Weber is the unit of magnetic flux. So this is Coulomb's law in magnetism. So it's quite similar to the Coulomb's law in electrostatic, where we have k to be equal to 1 by 4 pi epsilon naught. Here we have k to be equal to mu naught by 4 pi. So, and instead of q1, q2, we have m1 and m2. So that is the difference in this Coulomb's law in magnetism and Coulomb's law in electrostatics. Now in chapter 1, we have also learned about an electric dipole. So here in magnetism, okay, there is another term called the magnetic dipole. And this magnetic dipole is an arrangement of two magnetic poles of equal and opposite strengths separated by a finite distance 2L. And that is called a magnetic dipole. So an electric dipole, if we can recall, is defined as an arrangement of two equal and opposite point charges separated by a finite distance 2a apart. So here the distance between the two poles is 2L, whereas in electrostatics the distance between the two charges is 2a. So the figure of this magnetic dipole is shown, and as you can see here, there is a north pole and a south pole. Each have the same pole strength m, and the magnetic dipole moment of this magnetic dipole is defined as the product of the strength of either pole and the magnetic length of the dipole, and it is a vector quantity and is denoted by capital M. Remember in chapter 1 we have the electric dipole moment. Here we have the magnetic dipole moment, which is denoted by this capital letter M. and it is equal to m into 2l, and it is a vector quantity. Its direction is from south pole to north pole, and its SI unit is ampere meter square. So from where do we have this SI unit? From where do we get this SI unit? This SI unit is from the current loop taken as a magnetic dipole. Now, when a current flows through a conductor, then that conductor will produce a magnetic field around it, such that if we bring any magnetic materials close to it, those magnetic materials will experience a force of attraction or repulsion. So, in the last chapter, we have studied about Biot-Savart's law, and we have found out the expression for the magnetic field due to a current loop. So we know that a current loop will produce a magnetic field around it. Hence, this current carrying loop, it behave as a magnetic dipole. So a current loop behave as a magnetic dipole, and it has a magnetic dipole moment, and the magnitude of the dipole moment m of the current loop is given by m is equal to I into A, where I is the current flowing in this loop, and A is the area of the circular loop. And if the loop or the coil has n number of turns, then the m is equal to nia, and we have seen this quantity m is equal to nia in the last lecture, which is the torque experienced by the current loop. So here this m is equal to nia. It is known as the magnetic dipole moment of the current loop. And as you can see in the diagram, the current loop carrying current I is equivalent to a bar magnet, and the magnetic fields is the direction of the magnetic field lines is also shown in the diagram. So we have learned that a current loop behave as a magnetic dipole, and not just the current loop, the atom also is taken as a magnetic dipole. Now we know that an atom consists of a positively charged nucleus, and electrons are revolving around this positively charged nucleus, and this orbital motion of an electron around a nucleus is equivalent to a current loop. Now you know current is the flow of electrons, isn't it? So here also, since electron is in motion, orbital motion around the nucleus, then that is taken or is equivalent to a current loop, and the current is always opposite to the direction of flow of electrons. So in the diagram you can see that the electron of mass me, it moves in the one direction, and the current, it moves in the opposite direction. Hence here, since the atom behave as a magnetic dipole, it also has a magnetic dipole moment, and our aim here is to find the expression for the magnetic dipole moment of an atom. So here we consider again this electron revolving around the nucleus, and this electron is having mass me, and it's revolving in a circular orbit of radius r with a velocity v, where this current I is flowing in the opposite direction. And we let t be the time period. Time period means the time taken to complete one revolution. So t is the time period of the orbital motion of the electron. Then the current I due to the orbital motion is given as I is equal to E by T. Remember, this definition is from current from chapter 3. current is equal to Q by T. Here Q is equal to E, which is the charge of the electron, and T is the time period, which is the capital T. Now, from definition of velocity, we know that velocity is equal to distance divided by time. Hence, in a circular orbit, the distance that the electron covers in a time t is 2 pi r, which is the circumference of the circular orbit, or circumference of the circle. Hence, this v is equal to 2 pi r divided by capital T. Hence, the T, capital T, is equal to 2 pi r divided by v. Now, this r is the radius of the orbital path, and v is the velocity, the magnitude of the velocity of the electron. Hence, putting this expression of a t in the current I, we get I to be equal to EV divided by 2 pi r. And we have learned that the magnetic dipole moment of a current loop is equal to IA. Hence, here also the magnetic dipole moment of this current loop is equal to IA, and I, the current, we have found out to be equal to EV by 2 pi r. Hence, M is equal to EV by 2 pi r, and here A is the area of the circle, which is pi r square. So M here is equal to EV by 2 pi r into pi r square, and after simplification we get M to be equal to EVR divided by 2. Now in the next step, what we do is we multiply ME in the numerator and the denominator. So this MEVR is the angular momentum. Hence, your capital M is equal to E by 2ME into L, where L is the angular momentum. Now, since the magnetic dipole moment is a vector quantity, we can express this in vector form as M vector is equal to minus E by 2ME L vector. Minus here because the magnetic dipole moment is opposite to the angular momentum, and in the diagram it is shown that the angular momentum is in the upward direction, whereas the magnetic dipole moment is in the downward direction. Hence, we have this minus sign here. Magnetic field lines. Now again, if you can recall, in chapter 1 we studied about electric field lines, and electric field lines is defined as the path in which the test charge will move if it is free to do so. So here also the magnetic field line is the path along which an isolate north pole will tend to move if it is free to do so. Now we know that an isolate north pole does not exist. So here we're just imagining this north pole to exist, since magnetic field lines also, they are just imaginary lines. So here we imagine that the north pole, isolated north pole, exists, and magnetic field lines is the path along which the isolated north pole will tend to move if it is free to do so. And just like electric field lines, it has some properties. Magnetic field lines also, they have the following properties. Number one is that magnetic field lines are closed loop, extending through the body of the magnet. And here's one point of difference between the magnetic field lines and electric field lines. In electric field lines, uh, we may not have all closed loops, but in magnetic field lines, the magnetic field lines are always in a closed loop, unlike electric field lines where the field line is directed away from the positive or is directed towards the positive, and we can have a straight field line, but here the magnetic field lines are always closed loops. And the second property is that outside the magnet the field lines, they are directed from north to south pole. They always form closed loop. And number three, no two magnetic field lines can intersect each other. Again, this is similar to the electric field line. And the fourth property is that where the field lines are close together, the magnetic field is stronger, and where the field lines are well spaced out, the field is weak. That is also similar to the electric field line. And this is the figure of the magnetic field lines due to a magnetic dipole. And as you can see, it is directed outside the magnet is directed from north to south, and inside the magnet is along south to north, and they always form closed loops because an isolated north pole or an isolated south pole does not exist, unlike the positive charge and the negative charge. Earth's magnetism. Now, if you observe in a compass needle, the magnetic needle of the compass always orient itself or align itself in a particular direction. And this orientation of a magnetic needle of the compass in a particular direction at every place of the earth indicates that the earth behaves like a magnet. So it was assumed that a huge magnet is lying deep inside the earth with its south pole towards the geographical north and north pole towards the geographical south pole of the earth. So the earth can behave or acts as a magnet, and there's an assumption that there's a huge bar magnet inside the earth. And in the diagram, you can see the bar magnet having south pole and north pole. The south pole is towards the geographical north, and the north pole is towards the geographical south pole of the earth. Now, the presence of this magnetic field is very important as it acts as a shield from the cosmic harmful cosmic rays or particles radiating from the sun. So the magnetic field, what it does is it deflect or it deflect the cosmic rays or the particles, and it does not allow the particles to enter the Earth's atmosphere. Hence, this magnetic field, okay, is very important. And the presence of this magnetic field also cause the auroras that we see in the North Pole and the South Pole. Okay, or the auroras, or what we call the northern lights or the southern lights. Uh, the beautiful lights that we see in the North Pole and South Pole is because of the presence of the magnetic field. Now, the magnetic field at any point on the surface of the Earth can be described by three physical quantities, and these quantities are called the magnetic elements of the Earth's magnetism. And the three elements are number one, the magnetic declination. Now, this magnetic declination is the angle between the geographic meridian and the magnetic meridian, and it is denoted by theta. Now, what is this geographic meridian and magnetic meridian? Now, the geographic meridian is a vertical plane, okay, which pass through the geographical axis, and the magnetic meridian, it's again a vertical plane which pass through the magnetic axis. Hence, the angle between this geographic meridian and the magnetic meridian is called the magnetic declination and denoted by theta. And in the diagram, we see the magnetic meridian and the geographic meridian, and the angle between them is theta. The second magnetic element is the magnetic inclination or depth. Now, this magnetic inclination or depth at a place is defined as the angle in which the direction of the Earth's total magnetic field makes with the horizontal direction, and it is denoted by delta. Now if you look at the magnetic field of the earth, let us consider the point, okay, the north pole. Now in the north pole we see that the magnetic field is directed vertical towards the horizontal plane. Hence we can say that the angle between the direction of the field and the horizontal direction or the horizontal plane on the north pole or on the south pole is 90 degree. But if we consider the equator, the place in the equator, then you can see that the magnetic field is parallel to the horizontal plane. Hence the angle between the direction of the field and the horizontal plane or horizontal direction at the equator is 0 degree. So this magnetic inclination or dip is different at different places. Just like I've told you, in the poles it is 90 degree, and in the equator it is 0 degree, and in places between the equator and the pole it has different values. So that is known as the magnetic inclination. So the angle between the direction and the horizontal direction or the horizontal plane is known as the magnetic inclination. And in the diagram, again, we see the horizontal direction denoted by this line, and the direction of the field there, making an angle delta with the direction of this horizontal line. Then the third component, which is the horizontal component of the Earth's magnetic field. And this is defined as the component of the Earth's magnetic field along the horizontal direction, and it is denoted by BH. Now we know that the Earth's magnetic field is directed in different direction on the surface or at different places of the Earth. Hence we can resolve the component, the magnetic field, into two components, the horizontal and the vertical component. Suppose at any place on the Earth, the magnetic field makes an angle delta with the horizontal direction. Then this magnetic field B can be resolved into the horizontal direction, which is BH, and the vertical direction, which is BV. Hence, your B can be expressed or your in terms of BH and delta. So in the figure, if we consider the figure, we see that cos of delta is the base, which is BH, divided by the hypotenuse, which is B. Hence, your BH will be equal to B cos delta. And sine of delta is BV, which is the vertical component or the perpendicular, divided by the hypotenuse, which is B. Hence, the vertical component is equal to B sine delta. So here your horizontal component, which is the third magnetic element, is equal to B cos delta. Now delta we've known is the angle of dip. Now if we square and add the above two equations, what we'll get is b square cos square plus sine square delta, or b square into cos square delta plus sine square delta, and this is equal to bv square plus bh square. Now cos square delta plus sine square delta, this is equal to 1. Hence b square is equal to bv square plus bh square, and your b will be equal to square root of this bv square plus bh square. Now we can also find the angle of dip if we know the horizontal component and the vertical component. Now we can find the expression for this angle of dip by dividing 2 by 1. And on dividing equation 2 by 1, we have b sine delta divided by b cos delta, and this is equal to bv divided by bh, and bb cancel. Then we have sine delta by cos delta, which is tan delta. So tan delta here is equal to bv by bh. So here, if we know the vertical component and the horizontal component, we can find out the angle of dip, which is delta, and here delta will be equal to tan inverse of BV divided by BH. So these are the three magnetic elements which we can describe the magnetic field of the Earth.